This video will see me have some knowledge of secant method and generalized secant method for solving systems of nonlinear equations. In that second video, I used this source from Richard Brent, in which he covers other versions of secant method, citing also this book from Ortega and Reinbold. If this looks familiar, that's because I covered it in my earlier video on generalized Halleck's method. Both of these sources cited this additional source by Korganov. I'm not going to pronounce the French, but Korganov essentially explains that the problem with Newton's method is this need for having so many partial derivatives, but those can be approximated using divided differences. Their modified Newton's method uses 2 points essentially to create their Jacobian. The author then proves that this method can also be used for solving single equations and that its order is 1.618. This method, though, is not the focus of this lesson. Instead, I'm going to look at this paper by Robinson, which is also cited in both of these sources. Here's Robinson's approach. Firstly, he cites the Wolff-Bittner method, covered in my earlier video. The trouble, though, is that he uses Broyden, which he shouldn't, specifically citing this paper, which is Broyden's method, and I covered that in another video. But first, a little history from Ortega and Reinbold. Wolff-Bittner, where the generalized secant method was actually figured out by, of course, Gauss, because of course it's Gauss. There was also somebody else named Heinrich who never published their approach, and then Bittner and Wolff at the same time. Robinson notes the problem with Wolff-Bittner is that the more equations you add, the slower the convergence. Meanwhile, his approach has an order of 1.618 and is guaranteed to converge if you start close enough. Here is Robinson's approach, which I'm not a huge fan of the notation, but it is a 2-point secant method that solves systems of nonlinear equations, kind of similar to Korganov's approach. Let's try to simplify the notation, but first note that here H is any orthogonal matrix, so let's just replace H with the identity, and then I'll rewrite it to be much more simple. I let H be our multiplication against the identity, and then let J be this equation for our Jacobian, giving us a secant method approach to Newton's method. This also works for single equations too. If we let n be equal to 1, then we're essentially multiplying against 1, and we can rewrite and simplify our notation. Giving this form, which is Robinson's method for solving a single equation. Notice how this compares to secant method. It looks awfully similar. Here are the methods visualized on the same equation, starting with the same 2 points, and they are incredibly similar. The difference, though, is that their starting points are reversed. Here are the numeric sequences that we get. Notice how incredibly similar these sequences are. If we actually did start with the same 2 points in the same order, we get an entirely different sequence altogether. But now let's see how this secant method behaves in a nonlinear system example. This is the same one from my earlier videos that I've used. Notice that we'll now need 2 points because this version of secant method always requires 2 points. And then plug it into our equation from Robinson, giving us this value for H, which we then use as far as our Jacobian approximation, and then apply Newton's method, and we get value for x2. And then use our last 2 points to come up with the next approximation for H, and repeat the process. Here's our entire sequence converging in 7 iterations. I do want to point out the difference in notation between Stefanson's method, finite difference, and Robinson's method. They are essentially the same in their writing of the Jacobian, with the only difference being their value for H. Keep in mind, though, that I can be any orthogonal matrix, and I was the simplified version, but Robinson actually gives a different version. I'm going to use Ortega and Reinbold's notation because it's simpler. They use P times D, where P is the matrix that's written above it, and D is a specific diagonal matrix. This then lets the method be a little bit more efficient, but in my opinion, it's not worth it. Ortega and Reinbold leave one more remark in their notes and remarks section, stating that for generalized secant method, Various regular falsy type methods are obtained by holding fixed one or more of the auxiliary points. Essentially, you can make a generalized version of false position method from any secant method. For more about false position method, aka regular falsy, check out my earlier video. Some important takeaways from this lesson are that Korganov and Robinson created two other versions of secant method, and that they both have a convergence order of 1.618. They also both work with single equations. If you then fix one or more points, you get a generalized version of false position method. This then naturally leads to the question of what about a generalized bisection, which is going to be the next video in this series. The code that I wrote will be hosted on GitHub. And as always, thank you for watching. It was pretty difficult to find Korganov's textbook, and my librarians came through. There are still many more versions of generalized secant method, and if there's a specific method you want me to cover, definitely let me know in the comments. Again, thank you for watching.